Remember when you learned how to do multiplication in math class? You were probably taught some procedure for it, involving multiplying digits and adding subtotals. And if you're like me, it's likely you spent hours practicing that procedure on countless exercises. But have you ever considered how to multiply numbers with hundreds or even thousands of digits? Computers need to do this all the time, and making them do it efficiently has challenged some of the greatest minds for decades. In fact, the search for better ways to perform large multiplications gave rise to a young mathematics superstar, shaped some of the most popular programming languages, inspired new algorithmic techniques now used to train artificial intelligence, and even directly contributes to the security of your data as you watch this video. As numbers get bigger, it takes a computer longer to multiply them, but how much longer? That depends on both the size of the numbers and the algorithm used to do the multiplication. To fully appreciate the genius way that computers multiply big numbers, we'll first need to understand the basics of a concept called time complexity, which is a metric of how quickly a program runs. The idea of time complexity is to mathematically express the number of operations a program performs based on the size of its input. More operations for a computer translates to more time. In reality, it gets a bit tricky trying to define exactly what is one operation. There are a lot of different mathematical models for that. But for our purposes, operations are things like updating a variable, accessing memory, or doing some basic arithmetic on single-digit numbers. These are safe assumptions for this video. To start, I want to motivate an abstraction that we'll be using repeatedly. Suppose we have some algorithm that does a number of operations which is proportional to the size of the input to that algorithm. One nice example of this is the algorithm we all know and love for adding two numbers, since this simply requires scanning through both numbers once, column by column, and performing single-digit additions at each step. When we analyze the time complexity of this algorithm, that is, figure out how many operations it does for n-digit numbers, if we wanted to be really specific, we could try to meticulously count every operation and find an exact constant c, where the number of operations performed is at most c times n. But computer scientists have a neat way of classifying all expressions of this form. We would say t of n equals c times n is in big O of n. And actually, O of n encompasses every function t of n that grows at most proportionally to n. O of n is called a complexity class, and it consists of every function that looks like a straight line when you graph it. The reason why we make this abstraction is that it's useful when we compare algorithms. As an example, let's compare O of n with another complexity class called O of n squared, which consists of functions that grow at most proportionally to n squared. These functions are parabolas. For small values of n, it's possible for an O of n squared running time to perform better than an O of n running time. But as n gets large, the O of n running time becomes the clear favorite. And in general, when we compare different algorithms, we can tell which will perform better on increasingly large inputs solely by their big O classifications. Now let's figure out the time complexity of the multiplication algorithm you probably learned in elementary school. And I realized that there are a lot of different versions of this, so I'm going to show you the one I was taught, but just keep in mind that they all boil down to the same basic idea. With this problem on the screen, 654 times 321, we would first multiply 4 times 1 and store that result here. Then we multiply 5 times 1 and store that result next to the first one. Now we continue multiplying each digit of the bottom number with each digit of the top number, making sure to carry potential overflow and shift the digits over by one more place value for each new row. At the end, we add all the subtotals to get our final answer. In general, when both of these numbers have n digits, each of the n digits of the bottom number is multiplied with each of the n digits of the top number. So this algorithm would perform a number of operations proportional to n squared. This means an O of n squared time complexity. In algorithm design, it's always a potent question to ask, can we do better? Is it possible to multiply two n-digit numbers with a better time complexity than O of n squared? One of the world's most accomplished mathematicians, Andrei Kolmogorov, thought the answer was no. In 1960, the 57-year-old Soviet professor hosted a seminar at Moscow State University, where, among other things, he stated his conjecture that there is no multiplication algorithm with a time complexity better than O of n squared. After sharing his thoughts with his colleagues and students, he went home, probably never expecting to hear about it again. But little did he know, just mentioning his conjecture would alter the course of history. A 23-year-old graduate student by the name of Anatoly Karatsuba was attending the seminar and refused to believe that a better multiplication algorithm was impossible. He started working on what would become a huge breakthrough in computer science. Kolmogorov was in for one of the biggest shocks of his life. Amazingly, only a week later, Karatsuba notified Kolmogorov that he had disproved the conjecture. He discovered a faster multiplication algorithm. And not only is it faster, but it's faster by orders of magnitude. So how does Karatsuba's algorithm work? Kolmogorov and the general math community at the time were already aware of an alternative approach to multiplication. Say we want to multiply these two numbers, x and y. We can start by splitting them each in half, resulting in 4 smaller numbers, which we'll call a, b, c, and d. X equals 100a plus b, and y equals 100c plus d. So x times y equals 100a plus b times 100c plus d. And distributing the product, we can see this is equal to 10,000 a times c plus 100 a times d plus b times c plus b times d. It seems like we're worse off than we started. Now we have 4 multiplication problems to do instead of just 1. But the numbers involved in these 4 subtasks all have half the number of digits as the original numbers. What this means is that for each of these smaller subproblems, we can recursively do the same procedure, branching into further subproblems, only stopping once we're left with single-digit numbers being multiplied. In general, this works with n-digit numbers. Once all the subproblems are created, we can start evaluating them one level at a time, adding together the 4 recursive results from each step with the appropriate number of zeros appended to the ends. We keep doing that until we get a final answer. What stumped mathematicians at the time is that this recursive method isn't actually any better than the regular multiplication algorithm. It also has an O of n squared time complexity for n-digit numbers, and we'll see why a little later. But what Karatsuba noticed is that in the step where we expanded the original multiplication into the smaller subproblems, in this expression, we can rewrite a times d plus b times c as a plus b times c plus d minus a times c minus b times d. As an exercise, you can verify this for yourself. It may not be immediately obvious why this is a good thing. In fact, I'd encourage you to pause the video here and see if you can figure that out. First of all, take a moment to realize just how strange it is to add a plus b and c plus d. If you think about what this is actually doing, we're chopping up the digits of the original number into halves and adding them together. When would you ever do that? And even more puzzling here is it looks like the result is worse. Seemingly, we have to do 5 multiplications now instead of just 4. But what's so great about this reformulation is that we needed to compute a times c and b times d anyway. Using them an extra time here doesn't contribute to the number of subproblems. In fact, the number of distinct recursive multiplications has now been reduced from 4 to 3. I've highlighted each of them in their own color. We have a times c in red, b times d in green, and a plus b times c plus d in purple. It's not even so clear that reducing the number of subproblems like this is even beneficial though, especially since we have to do some additional work to add a plus b and c plus d, and also to subtract off a times c and b times d here. But this trade-off is worth it compared to doing another recursive multiplication. I'm going to prove that to you in 2 ways. In a couple minutes, I'll show you that this algorithm from 1960 is so good that many popular programming languages still use it today. But to mathematically see why this trade-off is worth it, we need to do some concrete analysis. Take a moment to read through the pseudocode here. Each time the algorithm is used, it branches into 3 recursive subproblems. The parts I've highlighted represent the 3 recursive multiplications we just saw a moment ago. Every time we do this, the number of additional subproblems created gets multiplied by 3. The kth split creates 3 to the k new subproblems. Importantly, in any one of these instances, the extra additions and subtractions we have to do only take an amount of work proportional to the number of digits in that instance. In fact, that goes for all of the computation besides the 3 subproblems of that instance. I'll let you pause here if you'd like and think about why that's true. And keep in mind that for the last line of code, the quote-unquote multiplication by powers of 10 is really just shifting digits since we're representing our numbers in base 10. Later, when I show you my actual implementation of this algorithm in Python, we're going to do everything in base 2, since that's how numbers are represented on a real computer. Remember, the numbers being multiplied in each subproblem have roughly half the number of digits as the problem that created it. So if the original numbers have n digits, the number of digits in each of the 3 to the k subproblems created by the kth split is n over 2 to the k. That means the amount of work done by any subproblem at the kth split is essentially a sum of a bunch of things that are all proportional to n over 2 to the k, which results in an expression that is also proportional to n over 2 to the k. So we can write it as c times n over 2 to the k, where c is some constant. The combined work done by all subproblems at the kth split is 3 to the k, the number of subproblems, times cn over 2 to the k, the amount of work for each subproblem. The number of splits is the number of times we have to chop the n digits of the original numbers in half before we end up with single-digit multiplication problems. This is log base 2 of n. Finally, we can write the total amount of work T of n performed by Karatsuba's algorithm as the sum of the work done at the kth split for each k from 0 to log base 2 of n. Some of you may recognize this as a partial geometric sum, which we can evaluate. And it takes a bit of algebra, but when all the dust settles, we end up with an expression in O of n to the log base 2 of 3, which is about 1.585. We get a time complexity that has an exponent better than the standard O of n squared multiplication algorithm by about 0.5. This might not seem like much, but in a few minutes, you'll see that it performs orders of magnitude better on large inputs. Notice, by the way, that if we replace these 3s with 4s, this would constitute the analysis of the known recursive approach before Karatsuba's improvement, the one that makes 4 subproblems. In this case, the formula would work out to be in O of n squared, as I mentioned earlier. I want to take a quick moment to pause here and reflect on how cool the result we just got is, because it kind of feels like it comes out of nowhere. Earlier in this video, when we analyzed the time complexity of the standard multiplication algorithm, there was a very straightforward reason why we ended up with O of n squared. We had to directly multiply n times n. But now, the exponent on n isn't even a rational number, much less an integer. And the way that it comes up is through some rather messy algebra to analyze a geometric series. I personally thought this was amazing when I first learned about it, because the intricacy of the analysis seems closely related to the ingeniousness of the algorithm here. And I find that this is not always, but often the case in algorithm design. It's almost as if the rules of mathematics are enforcing immense creativity for an algorithm to be an improvement on the obvious method. I promised earlier that I'd show you some empirical results too, so let's use some Python code to see the effect of this algorithm in action. Specifically, I'm interested in making a graph of the running time for each of 3 tests. The first test is the naive recursive algorithm, the O of n squared one. I've implemented it in binary so we can make use of bit shifting and we don't have to use any built-in multiplication or division. For those of you who are interested, I'll post a commented version of this code in my Discord server that fully explains how it works. But the bottom line is, you can think of this algorithm as a representation of pretty much any normal method of multiplication without some special trick. On the horizontal axis, we have n ranging up to about 6,000, and on the vertical axis, we have the time in seconds taken to multiply 2 random n-digit numbers on my computer. You can see we get a parabolic looking shape, which is to be expected because of the O of n squared time complexity. Next, I tested my implementation of Karatsuba's algorithm. When we graph the running time, you can see it absolutely crushes for increasingly large values of n. I mean, it's not even close. Something else we can do is try to estimate the degrees of these polynomial curves. If we instead graph the log of n versus the log of the number of seconds, the approximate slopes of these lines tell us the exponents on the dominating terms. I did a linear regression and found that these slopes are about 1.91 for the yellow line and 1.55 for the pink one, which matches our previous analysis that the yellow graph is O of n squared and the pink one is O of n to the 1.585. The final test, however, was the one I thought was the most interesting. This one simply uses Python's built-in multiplication operator, this star symbol. When we graph the running time on the same logarithmic plot, we get this. The point of interest here is that there's a sudden switch at about n equals 2 to the 7 or 128 digits, where the slope seems to change. That's because, for smaller numbers, Python is using what is essentially a version of the naive O of n squared algorithm. But the implementation is so well optimized that until the numbers get big enough, the bottleneck on efficiency is not the number of digits, but rather constants, which mostly depend on hardware. In fact, the slope of the initial segment of this bottom curve is very close to 0, meaning below a certain number of digits, there's almost no additional cost to multiplying larger numbers. And the naive algorithm is better for these inputs because it avoids doing the extra additions and subtractions that Karatsuba's algorithm has to do. But for larger numbers, Python switches to Karatsuba's algorithm. What's really fun is you can see that because the tail end of the bottom curve becomes parallel to the pink line for my implementation, meaning they have the same slope. Hypothetically, if we were to force Python to keep using the naive algorithm for larger numbers, eventually the limiting factor would become the number of digits, and we would eventually see the slope of the bottom curve match the steeper slope of the yellow line instead, which is why Python makes the switch. Karatsuba's algorithm is clearly much better than the naive algorithm, but can we improve upon it even further? Is it possible to multiply two n-digit numbers with a better time complexity? As it turns out, Kolmogorov's challenge from 1960 and Karatsuba's answer to it only a week later proved to be merely the start of a decades-long history. Most recently, in 2019, Harvey and van der Hoeven developed an algorithm that matches a conjecture by Schoenhug and Strassen that the best possible result is O of n log n, which is a complexity class we didn't talk about in this video. It remains unproven whether there could be an improvement on this. By the way, Volker Strassen later went on in 1969 to find a faster algorithm for multiplying matrices using very similar techniques to Karatsuba's algorithm. This brought the time complexity down from O of n cubed with a naive approach to O of n to the 2.81, leading to a long series of improvements. Now, these improvements are crucial to the underlying systems for training artificial intelligence models, which, if you didn't know, is fueled by lots of huge matrix multiplications. Going back to regular multiplication though, you may be thinking back to our experimentation from earlier and wondering why Python still uses Karatsuba's algorithm instead of one of these newest developments. In fact, I found out that Python does actually switch to the Thum-Cook or Schoenhug-Strassen algorithm for really huge inputs. But the short answer to that question, and the reason for all the switching between the methods, is that in the functions that describe the actual number of operations performed in these algorithms, the constants we ignore to get the big O bounds are enormous. So unfathomably big that the two most recent of these algorithms are often given the title galactic algorithms. The inputs would have to get so large before these algorithms start outperforming the quote-unquote worse ones that they would never be used in practice with any numbers describing real quantities on Earth. These algorithms exist purely as theoretical results for now, but theory is a tool that allows us to formalize and quantify improvement, and often leads to practical applications in unexpected ways. For example, consider a world before we had computers that could multiply numbers with mere hundreds of digits. Karatsuba's algorithm might have seemed like one of these results that only exists in theory, but now it's implemented in so many popular programming languages. And as one example, efficient multiplications with thousands of digits are now central to public key cryptography systems like RSA that keep your information secure when you write emails or browse the web. Despite its unassuming nature, the task of multiplying two numbers together has challenged some of the greatest minds for decades. Every step forward, from Karatsuba's elegant insight to the most recent galactic algorithms, expands the horizon of computation. Even the breakthroughs that seem far removed from practicality today could form the foundation for new innovations in the future. In the pursuit of furthering our understanding of the limits of computation and the world in general, it's crucial to have top-tier educational resources, which is why you should check out Brilliant, the sponsor of this video. Brilliant offers interactive lessons on a wide range of topics, from computer science theory to mathematics and more. Their hands-on approach is designed with first principles thinking and lets you build real problem-solving skills from the ground up. You can learn at your own pace with just minutes a day, and that small commitment adds up over a long period of time. If you want to learn more about algorithms and programming, there's a good chance you'd like this course on Thinking in Code, where you'll develop a solid foundation in the rudiments of programming. I'd like to extend a big thank you to Brilliant for sponsoring this video. You can visit brilliant.org/PurpleMind to start your free 30-day trial and get 20% off an annual premium subscription. You can also scan the QR code on screen or click the link in the description. I'm really excited to make more videos on computer science theory in the future, and if there are any particular topics you're interested in seeing covered on this channel, I'd love to read your comments about it below. With that, I hope you enjoyed and learned something. Thanks so much for watching, and I'll see you next time.